start to look at all. I read it over a few times, just all the steps I do, but I don't really follow it all. Oh yeah, that's right. What time is that? How's that thing landing? Not like a cable thing like we did that one time. Yeah.
Hello. Thanks. All right, is the audio at School of Minds okay?
Yep, I can hear you well.
All right, good. So I hope everyone had a good Thanksgiving. So right, there are only a handful of lectures left. So as you finish up quantum electrodynamics with the homework and getting a chance to look at how to do some regularization, I also wanted to at least introduce some topics that are helpful for understanding the real world. Quantum electrodynamics is, of course, pretty important, and that's certainly part of the real world. But another really important topic, which is not present in quantum electrodynamics, but is present in understanding the weak force, is symmetry breaking. And actually, most of the content for today's lecture, which is about spontaneous symmetry breaking, it's not just relevant for the weak force. That's probably the most important application to particle physics. But it's also a topic that's very, very powerful and important in condensed matter physics. And a lot of the theorems and things we'll talk about today were first discovered there. So we'll get to that. It's very general, so in that sense, pretty important. Right, so one of the core things, right, we saw in quantum electrodynamics was, there's a conserved charge, right? So there is some conserved the U1 symmetry, basically, is what gave us conservation of charge, can explain a lot. I mean, that takes you pretty far. But not all the symmetries of nature are preserved. So basically, it's sort of a funny situation because, at first glance, I'm going to talk about a symmetry, but then it's a symmetry that's no longer a symmetry at the end of the day. So in what sense is it a symmetry to begin with, right? It seems kind of strange. So what we mean by spontaneous, what's called spontaneously broken symmetries. So these are basically symmetries where the theory breaks itself. So symmetries of a Lagrangian that breaks itself. So that is to be contrasted with something that has explicit symmetry breaking. So let me say what I mean by these things. See if this works. Okay. So, right, like always, a good place to start when you want to understand some new theory is with the simplest sort of example, which would be just 5/4 theory. So that's what we'll do here too. So, sort of a generalized prototype. So by the way, this is sometimes called, just abbreviated, spontaneous symmetry breaking. Yeah. So our prototype for SSB, for spontaneous symmetry breaking, is a 5/4 theory, where basically I'm going to have just a theory of a multiplet of scalar fields, some n grouping of scalar fields. So I would have some kinetic term, which I'll write very schematically, and a mass term, and I can also have a 5⁴ sort of interaction. And what I mean by this vector of scalar fields is just I lump together n scalar fields and that's it. That's the whole theory, right? So if I have n equals 1, this is the normal 5⁴ theory we studied a bit. And all that this really is n copies of that, right? Because there's no weird terms. There's no phi1 squared times phi2 squared or anything like that. There's no specific, there's basically nothing that singles out any one of them as being special, right? They all have exactly the same interactions. So, and in particular, right, what kind of symmetry does this obey? I think we may have studied something like this in Peskin, really early on, in chapter 2 or something.
Right.
Is that right?
For that, yeah.
That seems sort of familiar, right?
Yeah.
Yeah. Did you have a question?
Well, just the symmetries is just the length of that.
Yeah, exactly. Right? So you could think, this is just, I could think of it in terms of spatial coordinates or something. If I have a vector that's of length n, if I'm in space dimension n, I have some vectors, then the symmetry is just the rotation group, right? Everything depends on the modulus, right? So that's the crucial thing. So if I'm just talking about lengths of things, right? Everything just depends on the length of the vector, then the rotation doesn't matter. You could rotate however you want. There are n ways to rotate, so the symmetry group in this case is just ON. Sometimes you might write SON, but the S is just for it being if it has unit determinant. So this exhibits some ON symmetry since you can rotate. Basically, since only the modulus enters into the Lagrangian. So before we talk about spontaneous symmetry breaking, let's talk about what explicit symmetry breaking would be. Right? This would be easy to just add by hand. You could, for example, so explicit symmetry breaking terms. From things like, what if I just added some mass term that was special just for phi 1 squared, or I added some funny interaction, that singles out one of them as being special, right? It doesn't have to be phi 1, this could be phi 2 or whoever. So I'm just saying there are a number of terms I could just throw in and say I have in the Lagrangian, but if I do that, this symmetry then gets broken. Right? In particular, right, if I only add one of these, it's broken down to ON minus 1, because I'm just singling out one of them. Right? If I added both of these, though, it'd be broken down to ON minus 2. Does that make sense, roughly? Because I'm just saying the other rest of the components are unaffected, so those are all the same. I can still rotate among them, and everything's the same. So that's the sort of symmetry that you'd have. All right, are there any questions about that idea? Just have a group of scalar fields, and the Lagrangian just depends on the modulus of this n-component vector. So it's just me saying I treat all of them the same, I can rotate them into each other. And explicit breaking is just, I put something in right in the Lagrangian that breaks that symmetry. Spontaneous symmetry breaking is going to be that we let basically the dynamics of the potential break the symmetry. And there's a big consequence in doing that. And at first it's very confusing, actually. It seems strange. So to basically have a theory that leads to spontaneous symmetry breaking, well, consider a mass term that has the wrong sign. It seems like a funny thing to do, but we'll see what the consequences are. However you spell spontaneous. That's why I always write SSB, then you don't have to worry about it. Too many vowels altogether. So we're going to study the same bi-fourth theory. But with the wrong mass sign. Or I guess I should just say opposite. Nothing wrong. It's naively wrong, I guess. So we'll write it out again so we can talk about it. Okay, so at first this seems weird, right? Because if I want to just interpret this in my normal way of doing things, this is, Lagrangian is the potential, the kinetic piece minus the potential energy, right? And the way we've been doing things, right? Negative mass squareds are really physically positive masses, right? So naively, looks like it has an imaginary mass or something. Right? Seems strange. But we know basically what to do I mean, if this was a quantum mechanics problem, instead of phi, this was x, we would know what to do, right? It's just a potential. So it just means, right, when this has a minus sign in front, it's fine for me to think of small oscillations, basically, around phi equals 0. But now, or in other words, when I talk about small oscillations, what I really mean is, what I've usually been doing, implicitly, is working in a vacuum in quantum field theory, where phi is on average 0, right? And we look at oscillations around that minimum. Those are the particle excitations that we do scattering with and all that. But this is a theory where we don't have that. So you get better intuition by looking at what the potential looks like. So let's just draw it. So it still goes to 0 at 0. Right? But now it doesn't make sense to expand around this point anymore. Now the theory will have to choose between one of these two minima. These are the true ground states. Right? In quantum mechanics, we would call them the ground states. In quantum field theory, we just call them the vacuum that the world chooses. So what we should do instead is expand, look at excitations around that, one of those minima. And which one the world chooses is ultimately due to some quantum fluctuations that choose, let us roll down to one or the other of these. But at the Lagrangian level, there's no difference, right? That's one way of stating our symmetry. Let me also clarify, right? Let me do first n equals 1 case, right? Let's make it as simple as possible. Otherwise, I have n directions of fields, right, to worry about. So if I have n equals 1, my n component thing is just one scalar field, right? So just have a simple one-dimensional potential. And instead of there being the symmetry group ON, right? The symmetry group in the case of just having one scalar field is just basically a discrete symmetry, right? It's basically just everything's unchanged by going between one or the other vacua. So let me call, by the way, you can find, so this, we have minima plus and minus v. So this is plus v, this is minus v, and this v you can find as square root of mu squared overlapping. Right, that's just from minimizing the potential. So, right, the point is now phi equals 0, not the ground state. So, you choose plus or minus v basically to expand around, to look for excitations. So in other words, what I mean by that is, what we should do is instead of working with what we're calling phi, we should work with some phi prime that's displaced from phi by just an amount v. Right? So instead of looking for little oscillations right around there, let's look for oscillations at one of these minima. And there's no obvious way to choose plus or minus, so we'll just choose plus v to work on, to expand around. So we should rewrite things in terms of some phi prime and put that in to our Lagrangian. So, right, the kinetic term is pretty boring, but I'll write it. So now we have a plus mu squared over 2, phi squared, and 9 to the fourth, phi to the fourth. And we want to just insert this expansion now. So we can keep, the expansion will get somewhat messy because of the phi to the fourths, but let's just keep up to quadratic terms. We don't need to worry about the phi to the fourth or phi cubed terms. So one thing that's going to happen, right, is that, so from both contributions, we'll have something that gives us something non-zero, right? Which is basically something that gives us non-zero, I mean, even for phi being 0. So that's just basically going to be the statement that, there's going to be some total energy contribution from the potential when you choose one of these minima. And that's fine, so like always, we'll basically just drop that. So I'll write out some of them, not all of them. And for the, lambda is minus. Right, the way you always do these things, right, is with whatever it's called, the Pascal's triangle or something. It's going to be the form like 1, 4, 6, 4, 1 for the coefficients. Right. So, right, you'll have these two constant pieces, which come with opposite signs. And I can put in also what is V, right? V, we know what it is. Depends on things in the Lagrangian. And so let me group together a similar term from the lambda term. So we have these two. And very importantly, the coefficients that are linear in phi, those are equal and opposite between the two. So those cancel. And mu squared over 2, phi prime squared, minus 3/2, mu squared, phi prime squared, and things up to phi cubed. All right, so we can read off what the result is. So we'll have some overall constant energy piece. The kinetic energy is unchanged because that's a derivative. And now we have the right sign mass term. So this seems pretty simple, right? We shouldn't be freaked out by having an opposite sign there. All that it means is that, because at the end of the day, when I do the expansion around the correct minima, I get the right sign mass term, right? It seems kind of funny that I don't have a 1/2 in front, but that's just what comes out. Instead of a mass mu, it's a mass square root of 2 times mu. So the shifted field has a mass phi prime has a square root of 2 times mu mass. So in general, the way to figure out what the real mass is to find the second derivative of the potential and just evaluate the potential at the minimum, at this special value called V. And the way to think about, right, what's going on here, I mean, we can sort of use our classical intuition that, the minimum of the potential is basically where the field is at rest. It's the vacuum, but the big difference in choosing this vacuum versus the normal one that we've been using is that now there's an expectation value for the value of the field. So we call that a vacuum expectation value, or just a VEV. So this thing V is called a vacuum expectation value, and that's basically what's happened in the rolling down of rolling down the hill. Now, everywhere in space, we say that this field has acquired a vacuum expectation value. So when this happens, symmetry is broken. And then phi acquires a vacuum expectation value or a VEP. So this example is helpful. I mean, it at least makes us not worried about having minus signs in our potential for the mass term. But things are very, very different when we go beyond n equals 1, and much more interesting. When we go to n equals 2, something really weird happens. And this generalizes to n greater than 2. All of a sudden, someone becomes massless. So the other big difference, so now let's go, so now we have a continuous symmetry for n equals 2 and above. So the potential in this case looks the same, but I just spin basically sometimes these types of potentials are called Mexican hat potentials. And it makes even more sense when you look at the n equal 2 case. So we have the same sort of shape, but now I imagine spinning this thing around. I don't know if that's clear. So this is the potential. Now that depends on two different fields. This is phi. Call that one phi 2, and this one phi 1. So you can see why it's qualitatively different, right? Now, right, in the n equals 1 case, it was one or the other choice, right? Just two possibilities and very discrete. Now, there's a continuous span of equal minima. And there are an infinite number of them in our way of counting before, right? So now we have a circle of minima. Ones that all have phi 1 squared plus phi 2 squared equal to mu squared over lambda. The same combination of Lagrangian parameters we had before. But now any one of them that satisfy that condition are equally good. So now the two vacua in n equals 1 case has grown up. They become a O2 symmetry. Right, this is basically the way of describing how you go around a circle is just rotating in 2 dimensions, right? We could call this U1 also if we wanted to, the symmetry group of the unit circle, or the symmetry group of orthogonal rotations in 2 dimensions. Right, so this is the same symmetry group of the Lagrangian in this n equals 2 case, right? We have just a 2-component vector of scalar fields. They're both equally good. We can rotate them into each other. And it's just a consequence of that Lagrangian that all of these vacua are equally good. So there's no way from the Lagrangian to choose one direction to point to. So let's just choose one. They're all physically equivalent. But to see something, let's choose that will lie all in this direction. will be our vacuum to expand around. And this is the same thing, mu over square root of lambda, and phi 2 is 0 on average. So I won't do the algebra, it's the same thing as what we did last time. I guess it's a funny looking mu, but that's a mu. So now we can again do the shift. Yeah, right. We do that and we find something funny. So everyone still has the same kinetic terms, we get the same vacuum energy term that doesn't matter for us. And phi 1 squared gets mass, and phi 2 doesn't. So this is a general thing that happens with these sorts of larger symmetries. So again, phi 1 gets a square root of 2 mu mass, and phi 2 is massless. So this is the first example of something very general called Goldstone's theorem. And physically, the reason why this happens, you could see by, again, looking at the Mexican hat potential, which is, right, there's a big difference in direction with this potential, right? If I'm sitting at the minimum, and I go up the hill, well, that really is acting like a mass, right? It costs a lot of energy to go up, so I'm going to want to fall back down. But if I roll along the gutter, so to speak, that doesn't cost any energy. That's the massless mode. That's basically why you get one massless degree of freedom that comes out of this. So that's the way to sort of think about. So phi 1 gets a mass, and it's because this is climbing up a wall. Mass is basically resist change, right? It's inertia. So, you know, if he's starting down here, he's not going to want to go up. And the phi 2 case is rolling along the gutter. And this is the big qualitative difference, right, that we mentioned. It's continuous. But this, and also I should say, right, I omitted higher order terms. So we're also just doing this at sort of the most basic level without looking at how, you know, does the mass still stay massless when I include renormalization effects or bigger, you know, fancier things, and it doesn't. So this is basically a first example of a general and exact phenomena, not something that's just true of perturbation theory or something. I guess we'll call it phenomena. When a continuous symmetry is broken. That's why it didn't happen in the n equals 1 case. So also, right, it may seem like this doesn't have a lot to do with particle physics because we don't have massless scalar fields around, right? The standard model doesn't have anyone who looks like they would be one of these bosons. So these are also called Goldstone bosons, the ones that end up not having any mass, so phi 2 in this case. But, so the small mass of the pion can be understood as an approximate Goldstone boson, like this phi 2 sort of example. I'll say a little bit about that. And also, in a very non-trivial way that we'll get to next lecture, it also provides a way for giving a mass to a vector boson. So this happens basically when you try to look at spontaneous symmetry breaking, but for a local theory. We're only looking at global symmetries. So we'll see how that works. You don't get massless scalar fields. You break a local symmetry, but something else happens. Basically, you give a mass to the vector. So I want to say a little bit about what this general and exact phenomena is, which is called Goldstone's theorem. I think Goldstone didn't live long enough to get the Nobel Prize, but Nambu, whose name is also associated with this phenomenon, won it in 2008, in part for the work related to this theorem. So let's remember what we know about global symmetries. So, the baseline thing is we have a continuous global symmetry. You get some conserved current, no third current. So someone called J is conserved, right? So, all right, remember too, in Noether's theorem, right? This is something that's true classically, and also true when we turn on quantum mechanics. But when we turn on quantum mechanics, now everyone becomes an operator. So our conserved charge is an operator too. So the way we're gonna, there's two, I think there are probably 4 ways or something of deriving this theorem. But the one we're gonna show is fairly subtle. It doesn't require any work, but just a little bit of thinking, not a lot of algebra. The Peskin has a different route that requires a bit more algebra. So check that out if you're interested in seeing it another way. But the way we're going to do it, I think, will emphasize how general it is, too. So in quantum theory, the Q charge that's conserved is an operator. So remember what it is. We do some integral over all space of the 0th component of that Noether current. And our Noether current is something built out of derivatives of the field, right? And since our fields are operator, of course the Q is also an operator. So I'll write down what this would be if we have some number of fields. Remember from Noether's theorem, we do take derivative with respect to the time variation of one of the scalars and multiply by how the thing, not at that, derivative of how the field varies under the symmetry. So this alpha is the thing that comes from our symmetry transformation. So remember, we're saying something like e to the minus I alpha phi for our symmetry. So you can convince yourself Q is an operator, and also in the language of the Lie algebra, Lie group stuff we were doing before, it's the generator of the symmetry. You could see that by just looking at, say, the commutator of what Q is, what phi, but also remember the baseline commutator that we use. And since we have n scalar fields, we should write it down in general if I have commutator. between one of the fields and the conjugate momenta in one of the other fields, that for bosons is a commutator, not an anti-commutator, and it's a delta function in space and in scalar field label. And this thing, the conjugate momenta, that's derivative of the Lagrangian with respect to phi dot. So you can see that Q generates the symmetry. From Q, looking at the commutator of Q and one of the fields. So I can just insert this integral for Q into the left-hand side. And also use, right, that, this part is basically pi, right? So I'm going to have my sum on the field, my integral. And now this is I am at x. X is my dummy variable of space. And we're doing this with a field at space-time point y. And we have this extra piece hanging around that's evaluated at x, because that's from Q, which is how the field changes under the symmetry transformation. So we can see how this comes back down to our baseline commutator, fundamental commutator, with the wrong sign though. So instead of phi comma pi, it's pi comma phi. So we have a minus sign. This becomes a delta function, so I can do the integral, and that's all there is. I get a minus I, and now this becomes evaluated at y, and also the n switches to an n because it's a delta. So this has exactly the right form, right? The commutator then of Q will shift phi a little bit. So this really does generate the symmetry. And another important thing to remember, so since Q is conserved, we also have its commutator with the Hamiltonian. Remember, everyone's an operator. I don't put hats on everyone, but everyone's an operator here. So because of I guess it was Ehrenfest's theorem, we know that the commutator is related to the time derivative of any operator. And this is a conserved thing, right? So this is 0. So this is basically what it means. We've talked about this relationship before also. This is just a reminder. But for the Hamiltonian to respect the symmetry encoded in Q, this must be the case, right? This is what it means to say that this is a conserved charge of the Hamiltonian. But now what we'll do, now we'll come to the symmetry breaking part. So suppose we have a vacuum that doesn't respect that's not invariant under symmetry transformation. So basically the true vacuum doesn't respect the symmetry associated with the Q. So I'll call this true vacuum, by the way. I'll call him some state omega. So omega doesn't respect the symmetry Q, which means Q acting on omega does not just return 0. So then we want to find what is the energy associated with Q acting on the true vacuum. Well, we know how to get the energy associated with some state. I just hit it with the Hamiltonian. Right? So in other words, just evaluate HQ on this, this vacuum omega. So this is the same thing. I can rewrite this as a commutator. So the plus sign would give me what I want, and then I have a minus QH, so I have to also add a QH. But I know what I can define basically what happens when I have H acting on the vacuum. Let me call that E naught. And this we already know vanishes by assumption. This sort of actually, this formalizes basically the idea of the gutter. So right, this is the energy, what is the energy associated with not just my original vacuum, but my vacuum that's been symmetry transformed? It's the same energy. It doesn't cost anything. This is the same thing as, I originally chose phi 2 is 0, but phi 1 gets all of the VEV in our n equals 2 example before. But that's arbitrary. So this encodes the gutter. Right? I mean, it's saying that the state omega and Q times omega are degenerate. They're equally good. So if you want, something you can always do once you have a vacuum is make a state out of the vacuum that has some momentum p. So this is the way to really see that it's massless. So you can always construct a state. State of momentum p, say. Vacuum. So we'll call these guys pi's, not to be confused with the conjugate momenta, but some state, some field configuration. So these are things where I give them some momentum with this plane wave insertion, and I still have my J0 acting on the vacuum state. So we already know what's the energy associated with Q acting on omega. It's just E naught. So this is now a state that has energy, whatever it is that's associated with having momentum P plus that E naught. And since what's the energy associated with pi of 0, since this has E naught energy, it must be the case, right, that the energy associated with having some momentum p is going to 0 continuously as p goes to 0. The only way that happens is if you don't have a mass. Right? If I did have a mass, I would have I took p going to 0, I'd have E of p is going to n as I go, right? So this, in other words, implies that there's something massless going on. It implies that these states satisfy E equals P. And that's really the statement of the Goldstone theorem. The spontaneous breaking of any continuous global symmetry will always give you massless particles, and those are sometimes called Nandu-Goldstone bosons. There are a lot of important caveats, right? Spontaneous symmetry breaking of continuous global symmetries. That gives you all right. Sometimes people just say Goldstone, sometimes people say Nandu-Goldstone. So that's really this Goldstone theorem. And they're always bosons. So there are a couple generalizations of the theorem. One we'll look at shortly is what happens when it's not just global, when it's a local symmetry. That'll basically be the Higgs mechanism. Another generalization could be, is there some way to get out massless fermions instead of just getting massless bosons? That seems to be pretty fundamental, that we're always getting bosons out. The only way to do that is if you have, basically you have to go back through the steps, and instead of having something that has commutators involved, you have to have something that has anti-commutators involved. And in particular, anti-commutators for the generator of the symmetry, which is unlike any type of symmetry we've studied. The only symmetry that has that property is called supersymmetry. It's a funny sort of symmetry where the generators act like fermions, basically. And in that case, you get out massless fermions, which are called Goldstinos, instead of Goldstone bosons. But I think it's clear from this simple proof that the theorem is really general and applies to bigger theories, to bigger symmetry groups. So there's a simple way to count Nandu-Goldstone bosons before we move on to local theories. So, right, the general counting is just to write. So if your Lagrangian has, say, n generators from the group G. So in our case, it was O2, right, which just had just gave us one Goldstone boson. Let's suppose your vacuum has an H generators associated with some other group. Then the number of Goldstone bosons you get is just the difference. The way to think about it, right, is that you want to find the number of conserved charges that don't annihilate the vacuum. And for each of those, basically for each of those, instead of having Q, right, we have some Q alpha or something, some grouping of different conserved charges. And for each one of those Q's that don't annihilate the vacuum, we get some other zero energy state. So that's basically the way to do the counting. I mean, this NH will always be less than NG, you'll remember. Be in any other example. Right, so these are actually the very first example apparently was discovered in a condensed matter context by Nambu. So this comes up also in studying ferromagnets. So let me just mention 3 examples. So in magnets, right, if you have magnets, you could think of as just some grouping of spins. And, if it's a non-magnetized ferromagnet, I should say, I guess. These exhibit an O3 symmetry, basically from the fact that the spins can be oriented in whatever way initially, and that gets broken when you apply some magnetic field. Both spins will get aligned and take on an average vacuum expectation value. It could take on an average total spin, right? So you break the O3 symmetry by applying a magnetic field, and that gives rise to massless spin wave states, which are actually observed. Right, the other thing, right, I didn't emphasize, but the power of that Goldstone theorem is that there's nothing that says that those phis have to be fundamental particles, right? These can be, effective descriptions of things. Another example that's closer to home for us is in QCD, in the theory of the strong force. So if you have basically with just 2 flavors, so the real world has 6 different quarks, but all that matters at lowest energies are the up and down quarks, the ones we're made out of. So that theory gets studied quite a lot. And in that case, there's an SU2 left, SU2 right theory. So if I turn off the theory of weak interactions, left and right-handed quarks are the same, and I have an SU2 associated with each of them, and that gets broken actually. Broken by the QCD vacuum, basically from the fact that quarks are so strongly interacting, they pair up and form bound states. So, and this being broken gives rise to the 3 ions, which are very light. They are not Goldstone bosons. So the 3 pions of QCD you can think of as what are called pseudo-Goldstone bosons. So even if the reason it's a pseudo-Goldstone boson is because this is an approximate symmetry. So this SU2 cross SU2 symmetry is broken by the explicit mass terms that the quarks have. If the quarks were truly massless, they'd be a real, the pions would be a real Goldstone boson, but it's only approximately true because it's basically the fact that the up and down quark masses are very small compared to the confinement scale of QCD. They're a few MeV, whereas the confinement scale is a couple hundred MeV. And the last important example is in local gauge theories, like the gauge group associated with the electroweak force, which we'll talk about. This gets broken, you may know this story a little bit, we think that at higher energies there was a hypercharge U1 that's sort of grouped together with a SU2 left of the weak force, and that was spontaneously broken down just to the subgroup that we know about at low energies, the U1 associated with electromagnetism. And in doing that, we didn't get massless bosons out, we didn't get massless Goldstone bosons out, because of the fact that this was a local gauge theory. It's not one associated with a global continuous symmetry. The fact that it's associated with a local gauge theory, though, means that what happened to those Goldstone bosons is that they got absorbed into basically the longitudinal modes of the vectors. So they gave masses to the vectors. So the counting, the degree of freedom counting still works out. That's basically where those Goldstone bosons went. So that's what I want to talk about now, is what happens now if we start thinking about spontaneous symmetry breaking in a local symmetry. All right, so anyway, so far, I think the Goldstone boson theorem is pretty cool and pretty fundamental. Are there any questions about that before we talk about local theories? All right, so we've talked a little bit about local theories. And there's a pretty neat way to see how important they are. So I think sort of this way that we're about to talk about them, I think it wasn't really until the 70s that people started thinking about gauge theories in this way, which emphasizes the importance of the local symmetry transformation. But gauge theories were really starting to be studied even in the 20s, apparently, by Hermann Weyl. So there's an interesting way to basically derive QED all just from the notion of there being a local symmetry transformation. So let's look at the Dirac theory, just the Dirac-Lagrangian. So what is the Dirac-Lagrangian? So it's some kinetic term for the fermion, and maybe there's a mass also for the fermion. So that's it, right? That's helpful, right? I mean, it's a Lorentz invariant construction of a fermion, but there's no interactions. We also know, right, that this is invariant under a global symmetry transformation, right? Basically, it's telling us that there's some conserved number, some conserved charge associated with phi. We know I can always do this sort of thing, multiply the field by some overall phase rotation and everything's the same. We know this is a global symmetry transformation. We emphasize that it's a phase. Global phase transformation. And by global, right, I really mean everyone gets multiplied by, at all space-time points, by the same theta, right? My field is something I can think of as being everywhere in space, but now I subject all the fields at all the space-time points to the same global transformation. So what about a local transformation? So we can see it doesn't work for Dirac because of that derivative. So let's just ask, though, for now, for no good reason really, but let's just ask. What about a local phase transformation? Which now can depend on the spins on the particular space-time point. So now depending on where you are, you get a different phase shift. So this is definitely not symmetry. So I could just look at the derivative of I EDI theta x psi. Right, so I'll get an I comes down because of the phase. I have to take the derivative of the phase. I still have the exponential. And the piece where I don't do a derivative on the phase. There's basically nothing else that's going to compensate that term, right? This term will disappear from, the minus I theta from psi bar, but, there's nothing really to get rid of this derivative of the phase, right? So basically, under that, a local phase change basically changes my Lagrangian to a part that has an overall derivative of the phase times the current associated with the Dirac field, right? Because basically, I looked at what's the derivative of psi. Now I have to put it back in the Lagrangian, and I did it with psi bar gamma. So that's how I get a psi bar gamma on that term. Okay, so first, before we talk about what I need to add to the Dirac equation to get it to be invariant under a local transformation, it's convenient to just pull out a factor from theta. A minus 1 over q factor. And instead to work with this thing we'll call lambda. So I'm just introducing someone new called lambda. So now, in other words, the symmetry transformation would be psi goes to minus iq lambda. Just making the substitution for what's theta. So this makes it even more suggestive. Now, what this is saying is that now the Lagrangian, under that transformation, will pick up, now there'll be a plus sign because I have a minus sign in front. There'll be a q times psi bar gamma mu psi. Something that really wants to talk to the Dirac current, and something that's proportional to the derivative of lambda. The derivative of lambda, we chose lambda because it makes us think of gauge transformations. And a derivative of lambda really makes us think of gauge transformations. So you could ask, what do you need to add? Do you add to the Dirac Lagrangian? To make the total Lagrangian invariant. Under a local phase shift. And the answer, kind of amazingly, is the QED Lagrangian. So if I write down my original Lagrangian, but I introduce one new field, which couples, even in the right way, a new field I'll call A, for him to absorb the annoying piece that's left over from how the Dirac field transforms, he has to transform in, basically in the same way so that this thing will be absorbed. So the only way that happens is if this will work if we posit that A mu under the same transformation goes to A mu plus derivative on lambda. And that's exactly what a gauge transformation is. So it's something surprisingly sort of deep in a way, that we're just bumbling around talking about phases, right? And thinking, okay, we know Noether's theorem is important for global symmetry transformation, but what about local phase transformations? Dirac doesn't seem to respect it, but if we start with Dirac and demand that the transformation be local, we basically have to have a new field that couples to a vector current of Dirac fermions that transforms like a gauge field transforms. So you have to have a photon around, and I also can't, the other important thing is I can't have a mass term for the photon. That would violate the symmetry. So somehow, right, we start with Dirac and we get a lot out. So that's part of the importance of gauge theories. It seems to be very fundamental, but also ultimately kind of confusing because your gauge choice is sort of a redundancy of our description, right? At the end of the day, the world can't depend on what lambda is, right? That's a choice of coordinate, basically. But still, right, it's gauge theories are certainly quite important. So let's see. So right, just so the upshot, you get out the massless vector with the correct QED coupling and everything. So I won't go through showing, but I think it's clear just from this. It's clear that a mass term would violate the symmetry transformation. You can write down that. So this you can generalize. I think really this wasn't until the 70s that people started thinking about how important these are. This is generalized to larger gauge groups. Here we just did it for U1, but this was generalized by Yang and Mills, and is important for understanding quantum chromodynamics and also for the weak force. So if you want to go on after this class and learn something about QCD, it's going to come back to these same sorts of arguments about local symmetry transformations. Things become more involved because now basically the generator of the transformation is not just a charge, it can be something non-abelian, and it becomes more involved. So, but the applications of the weak force are what we're going to focus on. So we'll do this next time. And naively, right, it's going to seem fairly strange because if we're saying, I impose local phase transformation as a symmetry that my Lagrangian has to obey, and I get that my vector field is massless. So that seems like it's not going to have a lot to do with the weak force because we know the weak force is mediated by 80 and 90 GeV bosons, things that are very not massless. But what comes to the rescue basically is basically Goldstone's theorem again. So Goldstone's theorem will give a mass to those through spontaneous symmetry breaking. Well now, basically what we'll see next time is spontaneous symmetry breaking for local tables. For local symmetry. All right, any questions? All right. So there's a lot, I think, in this lecture, with the Goldstone theorem and also the power of gauge invariance. So I should certainly recommend thinking about it and checking out Peskin. He has a good discussion too, which I mostly didn't follow, but that's sort of, you have more than one source of information about the same content. So, and also, right, check out the homework. That's due next Monday, the last day of class. All right. So otherwise, see you guys Wednesday. We'll see how the Higgs mechanism works.
I got a question about the homework.
Yeah.
So do you want us to start our derivation at the beginning of section 7.5 or at the beginning of the dimensional renormalization section?
So let me take a look, but I believe it's at 7.5.
Okay.
So I kind of forget how it's organized. Is the dimensional regularization not in that section?
That's a subsection of that.
Kind of go the wrong way first.
Oh, yeah.
Should we just not do that, or should we do that?
Let me take a look at it and clarify. So I'll send an email tonight about
Okay.
it.
All right. Thank you.
Yeah, sure. Let me make a note. Can I see your copy?
Yeah.
Because where is the final result? I guess here.
Yeah, back page they go. But they step back to here and then kind of redo it the right way.
Right. But this is the final
That's
result,
it.
basically.
That's
Yeah.
right.
Because before, well, I guess what you start with is essentially the 7.71.
Yeah.
I mean, because this is basically what you get from Feynman diagrams,
Yep.
and then, yeah. So that's all that I want. How do you go from 7.71
Yeah.
to 7.91?
Right. Okay.
Um,
Yeah, I think that's clear.
are you still there at School of Mines?
Yep, I heard that. So start with equation 7.71.
Yeah, that's right.
Okay. Perfect.
All right, great.
All right. Thank you.
Yeah, sure.
Makes sense.
All right, good, good.
Didn't see that. Which one? Oh, so for the